Swayam Prabha. Digital India. Educated India.
Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. I am Professor Anjali Pal from Civil Engineering Department. I am covering the environmental chemistry part, and this is my third lecture on acids, bases and salts. And in this lecture I will cover mainly the buffer, the mechanism of buffer action and how to select the buffer. Buffer, buffer is very important in chemistry in maintaining the pH. It is often required to carry out experiments in solution of steady pH. It is very useful in analytical chemistry as well as in biochemistry and bacteriology. If I tell you, I will tell you some question here. What is that question? Say for example, I have a solution of 0.001 molar HCl and it is stored in a open glass vessel. So, I have named it as solution A. I have kept it stored for quite some time, say for example 7 days. Then I measure the pH after 7 days. So, what should be the pH of that solution? I have already told you about the pH. I have given the concept of pH, that pH is nothing but the minus log of hydrogen ion concentration. And I already told you that HCl is a strong electrolyte, that means it will dissociate 100%. If that is the case, then the pH of the solution, that is solution A, if I calculate it, it is nothing but 1 into 10 to the power minus 3 minus log of 1 into 10 to the power minus 3, which is nothing but 3. That means pH will be 3. But after 7 days also, will that pH be 3? It is kept in a open glass vessel. That is the question. Will it be 3 or it will differ? Same way, 0.001 molar NaOH, if it is stored in an open glass vessel, it is called solution B, and if it is stored for 7 days, what should be the pH? If we directly calculate it, then pOH will be minus log of 1 into 10 to the minus 3. So, pOH will be 3. That means, pH is 14 minus 3, that is 11. But is that correct? Just direct calculation will give me the pH, or it will be different, something else? That is the question. The pH of the acid or alkali slowly changes and never gives a steady value. Why it is changing? Because first thing, sometimes the glass vessel, depending on the glass vessel, sometimes from glass vessel, if it is alkaline glass, some alkali may come out. So, if you keep some acid solution, that alkali will react with the acid and it will give different pH value. Sometimes in the atmosphere, because it is open glass vessel. So, sometimes from the atmosphere carbon dioxide may come, ammonia may come and it can dissolve in the water. So, it has the effect and it will change the pH. That means, pH will not be a constant, with time it will change. That is why they are not primary standard or secondary primary standard. So, what do we know about primary standard and secondary standard? We know primary standard is something which we can weigh accurately, which is not hygroscopic, which we can accurately measure, take the weight, and also if we prepare the solution, we can keep it stored for long period of time. That is primary standard. Strength is known, strength will not change with time, but for secondary standard we know with time it may change. The weight also we cannot take it properly like this. So, in the case of HCl and NaOH that we have prepared in the glass vessel is not a primary standard, because pH is changing. Now, here comes the function of buffer. Before going to that, I have two more questions. What is the pH of 0.001 molar NaCl solution? If I call it solution C, then what is the pH? And what is the pH of 0.001 molar ammonium acetate solution if we call it solution D, stored in an open glass vessel? This is very simple. You know that sodium chloride solution has the pH 7, it is neutral solution. So, it is 7. And what about this? Okay, for today you think that the pH is say x. I have not calculated it, say it is x. Now another question is coming. If we add 1 milliliter of 1 molar HCl to 1 liter solution of C, that means sodium chloride solution, what should be the pH? Initially it was 7 because it is sodium chloride solution. Now, I am adding 1 milliliter 1 molar HCl to 1 liter of this solution. What should be the pH? It is easy, because 1 milliliter 1 molar, now it is 1 liter. So, volume is increased 1000 times, and so concentration will decrease 1000 times. So, now it will be the HCl concentration will be how much? It will be 10 to the power minus 3, that means pH will be 3. But if we add same volume, same concentration, that HCl, if we add in 1 liter of solution D, then what should we see any change or we should not see any change? That is the question. Here we see change. Here initially it was 7, but now it is 3, huge change. But here what will happen? Here, say for example, I told you that ammonium acetate solution, it has the pH say x. Now, whether after addition of 1 milliliter HCl, 1 milliliter 1 molar HCl, what would be the pH? That is the question. Now, a solution of known pH which resists change in pH when a little acid or alkali is added, or when the solution is diluted, is known the buffer solution. So, buffer solution is a solution, some solution which will resist the change of pH. Means when you add HCl, it is supposed that it is known that it is expected that the pH will change. But if you use buffer, or if you add some HCl or NaOH to that buffer solution, the pH will not change. That is called the buffer action, and the solution is called buffer solution. Okay. Here in this case, the solution D, which is ammonium acetate, it is a buffer solution. So, when you add 1 molar HCl, 1 milliliter 1 molar HCl to this solution, this is ammonium acetate solution, pH will not change much, because very slight change may happen, but not much, not like this one, not like the solution C. solution C has changed a lot, but here it may have changed, but very slight change. So, that is why it is called a buffer solution and it is called the buffer action. This has enormous application in analytical chemistry, environmental chemistry, many process engineering. So, we have to know how it acts and what is the mechanism. Now, buffer solution, what is a buffer? Usually if we see the composition, then we will see the buffer solution may be two types, acid buffer and alkaline buffer. And if it is acidic buffer, then it is a mixture of weak acid and its salt. Example, acetic acid and sodium acetate. So, it is a mixture of two things, one is the weak acid and another is the its salt. Okay. So, if it is weak acid is acetic acid, then it is another thing should be there, that is its salt, that is the sodium acetate. And if it is a alkaline buffer, then it should be a weak base and its salt. Example, ammonium hydroxide and ammonium chloride. Or it can be a salt of weak acid and weak base. Just previous slide we have seen that ammonium acetate is nothing but a salt of weak acid and weak base. So, that is also a buffer. Now, if I consider the acid buffer, then consider a solution of a mixture of acetic acid of concentration. This way we write the concentration, right, within the third bracket. So, this is the concentration of acetic acid and the concentration of sodium acetate is this one. Where sodium acetate is complete, we know that salt is completely ionized, either it may be a salt of strong acid weak base or weak acid strong base, whatever may be, salt will be completely ionized. So, sodium acetate will be completely ionized and acetic acid, which is a weak acid, will be partially ionized. Okay. Then we can see what will happen. Hence, the acetate ion that is present in the medium, the mixture of acetic acid and sodium acetate, we can tell that the acetate ion concentration present in the solution is the total sodium acetate concentration, because the dissociation of acetic acid is very less compared to the dissociation of sodium acetate. Sodium acetate fully dissociated. So, most contribution is coming from the sodium acetate. Okay. And we can write the acetate ion concentration is nothing but the concentration of the salt. So, because it is a weak acid, we must consider the equilibrium. So, H acid, which is acetic acid, is nothing but H plus ion into acetate ion. Okay. And Ka, that is the equilibrium constant, is nothing but H plus ion concentration into acetate ion concentration by HAC concentration. And if we just change the sides by changing the sides of H plus in left hand side, then we will get this equation, H plus ion concentration is nothing but Ka into HAC concentration by acetate ion concentration or Ka into acid concentration by salt concentration. Now, if we take into logarithm term, then minus log of H plus ion concentration minus log of Ka, which is nothing but pKa, and minus log of H plus concentration is nothing but pH. So, pH is becoming pKa plus log salt, this will be just reversed. So, salt by acid. This is known as the Henderson equation. This is a very important expression for a buffer solution. pH of a buffer is, in case of acidic buffer, pH of a buffer is nothing but pKa. What is pK? Is the pK of that particular acid plus log salt concentration by acid concentration, and this is Henderson equation. Now, the buffer capacity. So, I told you, if you remember, that buffer action will be remaining in some range. It is not the whole range of pH, it will not act in that way. Not only that, buffer only can resist the change when slight amount, little amount of acid or alkali is added. It is not like you will add in 1 liter of buffer solution, if you add say 100 milliliter of strong acid solution, then the pH will be unchanged. It is not like that. Small amount of acid or small amount of base, if you add to the buffer solution or to a solution which contains buffer, then the change of pH will be not there, means it will resist the change. Okay. This is very important. So, buffer capacity is very important. Buffer capacity is maintained for mixtures ranging. What is the range? We have seen in the last slide that pH is equals to pKa plus log salt by acid. This proportion is very important. So, buffer capacity is maintained for mixtures ranging 10 salt is to 1 acid or 1 salt is to 10 acid. That means 10 is to 1 or 1 is to 10 for salt and acid, that ratio. That means pH is nothing but pKa plus minus 1, because log term is there. So, that is why it is coming plus minus 1. So, this is called buffer capacity. That means in that range of pH, say for example, acetic acid. If we think about acetic acid, we know, I already told you that for acetic acid pKa is 4.74. Say for example, so pH is equals to 4.74 plus minus 1. So, it will be within the range of 3.74 to 5.74. In that range it will be valid. It is not like the whole range of pH, it will be valid. Now, why it is happening, how it is resisting the pH, that is also very interesting and important. So, mechanism of buffer action. I have already told you that in the acidic buffer what is there, acetate ion is there. So, when you add the H plus ion, it will immediately combine with acetate ion to form the undissociated HAC molecule. If you add little amount of alkali, then it will react with the HAC to form the acetate ion and water. In this way, the addition of H plus, of course, small amount or OH minus will be consumed in some way, and it will keep the pH of the medium almost constant. It is not exactly constant, it is almost constant. Very small change you will observe. You will observe small change, not significant, small change you will observe. Similarly, for a buffer mixture, alkaline buffer, I have taken the simple example ammonia and ammonium chloride. For ammonia and ammonium chloride, it is an alkaline buffer. We can tell that ammonium hydroxide will be dissociated, it is weakly basic solution. So, it will be dissociated in ammonium ion and OH minus ion. So, we have to consider Kb in this case. Kb is equals to ammonium ion concentration by OH into OH minus ion concentration by ammonium hydroxide concentration. So, changing the slides, we will get this equation, and ammonium ion concentration is the total ammonium chloride, because the contribution of ammonium ion from the ammonium hydroxide very small compared to this one. That is why ammonium ion concentration is mostly from the salt. So, it is the salt concentration, and OH minus concentration here the same equation as we applied, similar, not same equation that we applied for an acid. In this case it is the in terms of Kb it will come, and in terms of POH it will come. So, POH equals to pKb plus log salt by base. This is also Henderson equation, and the mechanism will also be same way as it has been explained in case of acid. Okay. If you add acid H plus, then what will happen, and if you add OH minus slight amount or small concentration, small amount, then what will happen? This will be very similar to this one. Now, buffer solution, buffer solution, the natural buffer in biological systems, in body there is also some buffer. In our body system also you see that many reactions are happening, enzymatic reactions are happening, they need controlled pH. In our system, in our body, the controlled pH is very much necessary, but here we are not we do not have any ammonium chloride, ammonium hydroxide, or we do not have acetic acid and sodium acetate. In the biological system mostly it is carbonate buffer or phosphate buffer. We know that blood pH is 7.4 approximately. Now, one application of buffer solution, you have already those who are from chemistry background or who are from environmental engineering background, we all do the hardness determination, right. And in the hardness determination we always use a buffer. If you remember, what is that buffer? That buffer is the ammonium chloride, ammonium hydroxide buffer. And why it is used? It is used because we need to keep the pH in the range of 9 to 10, so that the reaction is complete. Okay. If the pH is not maintained, then the reaction will not be complete, and the determination of hardness, that is calcium ion concentration and magnesium ion concentration, that is multivalent cation concentration by EDTA. You know the determination, in the determination we use the EDTA solution, and in that titration, if the pH is not maintained in that range, then the reaction will not be complete. Now, how to design a buffer? This is a very important thing, how to design a buffer. To design a buffer, we have given one example here. To design a buffer, say I need a buffer solution, I need to keep the pH in this range. So, I need a buffer solution of pH 4.60. Now, there are so many buffers, we can choose different acids, we can choose different bases, we can choose different salts also. How we can decide which one we will use for our purpose? Okay. Now, if we see that if we are to design a buffer of pH 4.6, first we have to see which acid we will take, because it is acidic buffer we have seen, this is the below pH 7. So, it is acidic buffer. Now, pKa, because the pK values or K values of each acids, means the weak acids are enlisted, okay, at 25 degree centigrade. So, we can easily find out. So, pKa of acetic acid we know 4.74 or 75, and then plus minus 1, the buffer capacity is plus minus 1. So, if we go plus 1 or minus 1 of this 4.75 value, then it will remain in this range, is not it? 4.6 will remain in this range. So, we can tell that this buffer is suitable for this one, for our purpose. Now, what will be the, so we know the pKa value, but what should be the salt, that ratio, that acid and salt ratio, okay, that we have to decide. Now, here you see the, if you remember the Henderson equation, then we will see that this is the term that we have to decide. Now, pKa minus pH is 4.75 minus 4.60, because we want a pH of 4.60. So, 4.75 is the pK value minus 4.60 is equals to 0.15. So, this ratio should be 1.4, 1.4, okay, 1.4 log, this is the log term, na? If you remember the Henderson equation, then there it is the log concentration of salt by acid. This is this one. Now, what is the just ratio? Not here, log term is not there. Okay. So, concentration of acid by concentration of salt, this should be 1.4. To design a buffer of our purpose pH 4.60, the ratio will be 1.4. So, we can choose the ratio, we can choose the concentrations, but only thing the ratio should be 1.4. It may be, you see, we can do by choosing sodium acetate 1 and acetic acid, sodium acetate 0.1 and acetic acid 0.14, or we can choose 0.2 mole of sodium acetate and 0.28 mole of acetic acid. We can dissolve it in 1 liter. So, concentration will be like this, molar. Now, here you see the ratio is coming, here also the ratio is coming. So, you can choose either one, this combination or this combination, even you can try other combinations also. I think you have understood this part, because first you have to see that which buffer we have to take, which combination, and then we have to decide what is the concentration that we have to take for the salt and the acid. Thank you. Thank you for listening to today's lecture. I hope you have understood. Thank you.